Modern artificial intelligence hardware faces a widening gap between its ability to process information and its ability to move it. We have built processors capable of executing trillions of operations per second, but the physical pathways supplying them with data have not kept pace. This chart shows the divergence in hardware scaling over the last 2 years. While AI compute power grew 3 times over, memory bandwidth increased by only 1.6 times. This delta is the memory wall, a structural bottleneck that processing power alone cannot resolve. For large language models relying on the transformer architecture, this structural imbalance becomes the primary performance constraint during the inference phase. In data center operations, inference is the actual cost center. While training happens once, inference, the act of a model generating a response for a user, happens billions of times, and it is far more sensitive to memory limitations. Because the model must access its entire weight matrix to produce each individual word, the deployment of these models is now constrained almost exclusively by data transfer speeds. In response, the industry is splitting into 2 distinct architectural paths: specialized SRAM-first language processing units and HBM4 stacks that integrate logic directly into the memory. As while compute scaling hits these physical limits, the future of AI economics increasingly depends on whether we can shatter the von Neumann bottleneck. To see why inference is so difficult for standard chips, we have to look at the mathematical framework for performance constraints, the roofline model. This is the roofline model. It plots maximum attainable performance, the chip's raw compute, on the vertical axis, against maximum memory bandwidth on the horizontal axis. A chip's performance is limited by this equation. The intersection where the slanted bandwidth line meets the flat compute roof is the knee point. It defines exactly when a workload moves from being compute limited to being memory limited. When compute density increases without a proportional leap in bandwidth, that knee point shifts up and to the right. This expands the memory bound region, forcing more operations to sit idle while waiting for data. We can map the 2 phases of LLM inference directly onto this chart. First, the prefill phase, where the system ingests your prompt and processes it all at once. Prefill is a massive compute-dense matrix multiplication. Because it is highly parallel, it sits at the top of the chart, where GPUs can operate at maximum efficiency. But then comes the decode phase, the sequential generation of each word in the model's response. For every single token produced, the system must read the entire weight matrix and the conversation's KV cache from memory. This massive data-to-compute ratio places the decode phase strictly inside the expanding memory-bound region of the roofline chart. On a standard GPU, this means the massive compute cores spend most of their time starved of data, waiting for the memory to respond, an inefficiency that drives up the cost of every token served. The first way to bypass this bottleneck is to eliminate the need for off-chip memory fetches entirely. A standard GPU stores its model weights in off-chip HBM stacks. Fetching a 70 billion parameter model from those stacks across the die boundary takes roughly 21 milliseconds. The Groq 3 LPU architecture removes the HBM stacks and DRAM controllers. Instead, it places a 500 megabyte flat SRAM mesh directly on the logic die. The weights never leave the processor. This configuration achieves 150 terabytes per second of memory bandwidth, roughly 45 times the bandwidth of an H100's HBM3. In operational terms, the time required to load the model weights for a single token drops from 21 milliseconds to just under half a millisecond. Because the memory is directly on the die, the LPU system can utilize deterministic execution. It executes a fixed data flow graph, where every clock cycle does the exact same operation. This removes the need for prefetching logic or speculative execution, which adds latency on standard GPUs. This efficiency is visible in the power metrics. While a standard GPU might deliver around 4.3 tokens per watt for a dense model, the LPU design targets roughly 150. The trade-off is total specialization. The SRAM approach gives up the flexibility to train models or process prefill-heavy workloads to achieve maximum efficiency in steady-state generation. The second path keeps the memory off-chip, but transforms it from a passive storage component into an active participant in computation. This 3D cross-section shows the architecture of HBM4. It doubles the interface width of previous generations to a 2048-bit bus, allowing for a massive increase in throughput without requiring higher clock speeds. The shift in HBM4 is in the base die. Rather than using standard memory manufacturing, companies are now building this foundation on advanced 5-nanometer and 12-nanometer logic nodes. This change has forced a restructuring of the industry, with memory manufacturers now outsourcing these critical base dies to specialized foundries like TSMC. This logic die allows the memory stack to act as an active coprocessor, handling its own data routing and thermal management before the information even reaches the main GPU. This integration is part of a larger pivot toward hardware, where memory and compute are no longer separate. The patent landscape for 2026 shows a concentration of research into compute and memory and processing in memory architectures. Princeton University holds a dominant patent position in scalable CIM arrays, which use tiled macros to perform arithmetic logic directly within memory arrays. This research is supported by a thicket of international patents focused on embedding these operations into memory bit cells like SRAM and non-volatile FEFET devices. Technologies like HBM4 and CIM are physically dismantling the separation between computation and storage, specifically to resolve the decode bottleneck. This hardware specialization raises a system-level question. How can a data center leverage both compute-heavy GPUs and bandwidth-heavy LPUs at the same time? The answer is that the monolithic approach to inference is being replaced. Because prefill and decode phases have opposing hardware needs, they no longer have to happen on the same chip. This has led to the adoption of disaggregated inference, a system-level architecture designed to scale LLM deployment by separating these two phases onto different hardware tiers. In a disaggregated system, a single user request travels through two different specialized environments. The request first hits a GPU cluster for the prefill step. The GPU uses its massive teraflops to rapidly process the input prompt, creating the KV cache that represents the prompt's context. That cache is then handed off over a high-speed fabric to a specialized LPU or CIO rack. Here, the decode step begins. The bandwidth-optimized hardware takes the cache and generates the sequential tokens of the response, firing them back to the user at a speed and energy efficiency that a general-purpose GPU cannot match. While this adds complexity to the software layer, which must coordinate this handoff without visible latency, it enables a massive increase in total system throughput. By routing each part of the inference task to the hardware best suited for it, data centers can achieve a significant improvement in throughput per watt. Industry leaders are now treating the entire data center, not just the individual chip, as the primary unit of compute. This architectural pivot provides a pathway to sustain inference efficiency even as the next generation of reasoning models continues to grow in complexity.